Okay, so for calorimetry, specific heat capacity, they define as the amount of heat it takes to raise the temperature of a substance. And by substance, that could be like water, air even, granite, metal, like literally basically anything. To raise that by, they say, 1 unit. Now, in chemistry, so for our purposes, when we're talking 1 unit, think 1 degree Celsius. Okay? And if something has a low specific heat, that means it's easy to warm up. So an iron frying pan is very easy to heat up, so it has a very low specific heat capacity. So 0.45, and you don't have to memorize these to be sure. That's just kind of, it's a reference table. You're given these values. Compared to water, which has a very high specific heat capacity. Or if you're cooking in like an earthen pot, earthen pots have a very high specific heat capacity. So to raise, like if you put water in both of these, it would take much less energy, much less like gas. The gas bill is much lower to raise water to the same temperature in the iron frying pan than in the same amount of water in an earthen pot. Now, metals have a very low specific heat capacity, and that should make sense to you, and I want you to know that. Why would that make sense, that metals have a very low specific heat capacity?
They absorb like easier than
Yes, they're able to, well, I don't think absorb heat easily, maybe is the best way to put it. Well, sure, they absorb heat well, but why? Why would they absorb heat well? What makes them able to absorb heat well? See, others see. What's that? Say surface area.
smaller like
No, not so much that.
density?
Oh, no. It's a good thought. It's very felt no. They are good conductors. Okay. Now, remember, conductors mean they conduct electricity well. But what makes them good conductors of electricity? Like if we're kind of, and this is just good final exam review stuff, right? Why are metals good conductors of electricity? What even is electricity? What are we talking about when we're talking about electricity? Electrons moving, right? Okay. So what about metals makes them good at moving electrons? Ethan, go ahead. Yes, it has to do with the molecule, right? So we went over like the different models things have. We talked about the sea of electrons model. So the idea of the sea of electron model for metals is metals want to lose their electrons. The reason, that's why they form these positive cations, like if you look on our periodic table in the class. The reason why they want to lose electrons is because that will then make them have a full valence shell of electrons, a full outside shell of electrons, and they'll be stable. So because metals are able to lose their electrons really well, they end up having this sea of electrons, and that sea of electrons, those electrons, they don't belong to any one metal atom, so they're free to move across that metal surface, which makes them good conductors of electricity, and it makes them conduct the heat well, right? Then the heat can move throughout the material very quickly. All right, now water has a very high specific heat capacity. Now, why is that a good thing? Like, why would you want water to have a high specific heat? High specific heat means it takes a lot of energy to warm up water. That is crucial. Think of the opposite. If water had a very low specific heat capacity, next.
We don't want like our blood boiling.
Exactly, right. Like, I don't know if you're like, if you say someone's blood's boiling, it's like they're mad. It's like literally like imagine if like, imagine you're just like tanning, right? And water had a very high, like a low specific heat capacity. You would just evaporate, right? There would be no ocean, right? Water would evaporate very easily. So I guess what I'm trying to get at is there's less evaporation. And that enables life to happen. That's why we're all living things are mostly made of water. All right, so yeah, so different consequences of this stuff, but moving on to more of what you would see on the final as far as like calculations and stuff. There's something called the heat equation. So the heat equation, we call it Q equals mc delta T, where Q stands for heat energy. Now, You need to know the units, so make sure you start that down. Know units. In other words, I want you to know that you always measure heat in joules. And that should be familiar to you based on last unit, right? That y-axis was we would measure things in heat, like the heat content or energy, and you would see kJ a lot of the times. That's kilojoules, but it's still joules. Kilo is just 1,000, right? It's just a bigger form of joule. And then there's mass. Mass of your sample. We measure that mass in grams. C is your specific heat. I want you to know these units. So joules over grams degrees Celsius. So this C, this is what we talked about on the last slide. So how easy or hard it is to heat something up. And then delta T, change in temperature. Remember that triangle, you say that as delta. Delta always in science is final minus initial. So in this case, because it's delta T, T is temperature, it's the final temperature minus the initial temperature. Okay. All right, so I'll show you kind of a sample problem. So these two problems, this is really what I need you to know for the final exam. You will see a problem very similar to these two. You know how to solve it. And it's really not too bad. Yeah, I know the formula, Q equals MC delta T. It's just identify your variables and then solve for the unknown. So 26.5 grams, what would that be? Which of those letters? You say it. It's your mass, it's your M. Okay. With a specific heat of 0.283, so what would that be? It's your C. Good. Is heated from 15 degrees Celsius to 30 degrees Celsius. So this one's a little bit trickier because there's two numbers there, but this is related to your delta T. Where remember delta T is final minus initial temperature. So what's the final temperature here? 15 or 30? 30, right? Okay, good. 30 degrees Celsius. Initial's 15 degrees Celsius. I don't know why I wrote it that way. So delta T equals 15 degrees Celsius. Okay? Sometimes they'll just give you delta T. They'll tell you the change in temperature. Other times you have to calculate it. Most of the time you have to calculate it. Just like we did here. All right, so then they're wanting to know how much energy was used in the process. So which of these letters do we have to find? Q, right? This energy, that's your Q. Energy, heat, they're technically not the same thing, but you could think of them as essentially the same thing. They're very, very close. Very similar idea. So Q equals MC delta T. Q equals your mass, 26.5 grams. Now, I want you to write the units because your final is all multiple choice, but I could give you the correct answer, the correct number, but there could be two answer choices, or even three, with the same number, but I changed the unit on you. So I'm going to show you how you keep track of the units. So let's keep going. Then times 0.283 joules over grams degrees Celsius. And then our delta T, we solved that. That's 15 degrees Celsius. So, all right, so you do 26.5 times 0.283 times 15. And if we do that, you would get 112. Now, what would the unit be there? Because again, you have multiple answers at 112. Yeah, Rebecca, go ahead.
Is it J over grams degrees Celsius?
Nope, that would be the unit for specific heat for your C. There's two ways you can know. You could either just memorize it, or you could solve for Alex. You got it? Joules, good. So you could have memorized that your Q is always in joules. You can memorize it that way, or, and this is more ideal, thinking back to stoichiometry. Whenever you were canceling out units and stuff, what was the opposite of multiplication? Division. So if you see a G here, G for grams, and you see a G on the bottom of that fraction, what happens? They cancel each other out, right? So that and that, they cancel. And then here, you have, you're multiplying by a degree Celsius, but then on the bottom of the fraction, you have a degree Celsius, so those cancel. So that's why the answer is in joules. Joules is the only unit that didn't cancel out. Make sense? All right. As I said, I don't think it's too bad. Now, they can change which variable they give you or don't give you. Meaning, if you look at the second one, now they're asking us, what is the specific heat capacity? So that's our C. So our C is the unknown here. And they're telling us the mass, M, is 250. And they're telling us our Q is 402 joules. And then, got to calculate our delta T. Delta T, what's my final temperature? Delta T is 12. That will be correct, but how would you get there? Like, what's the final temperature, Ethan? 22. Yeah, 22 minus 10. Good. 22 is the final. 22 degrees Celsius. Minus 10 degrees Celsius, that gives you 12 degrees Celsius as your delta T. All right, so plug in and then find the unknown. So we know our Q now, and I'll do it a little bit bigger up here so you can see it better. We know our Q is 402 joules. We know our M is 250 grams. We don't know what our C is, but we know our delta T is 12 degrees Celsius. So then let's solve for our unknown, solve for our C. So you would want to do 250 times 12. 402 joules equals, what's 250 times 12? 3,000? Yeah, 3,000. And then, now what are the units there? 3,000 what? What are the units? You're a little unstable in here.
Grams.
Grant, no.
What? The Celsius cancels out, doesn't it?
Why would it cancel out? This C is not the degree Celsius C, nor is on the bottom of a fraction. Grams times degree Celsius, good. Grams times degree Celsius. Okay. And then you have the C, which is specific heat capacity. That's like your X. Okay. You could put X there for all, like if that feels better to you. So then we're going to divide both sides by the 3,000 grams degrees Celsius. And we would get our C equals 402 divided by 3,000, which is 0.134. But again, what are the units? Could have multiple options that are 0.134. Becca, can you got it? Yes, good. Joules divided by grams degrees Celsius. You could either memorize that that's going to be the units for specific heat, although, and for us it will be, but technically if you're doing like AP Chem, they can change these units up on you, right? Let's say they give you the mass in kilograms, like you can have a specific heat written in slightly different units. But if you're looking at it mathematically, because you're going to divide both sides by 3,000, so if I do that, divide both sides by 3,000, these cancel, but then 402 divided by 3,000, that's 0.134, and then you have joules divided by grams degrees Celsius, which you then see right there. Okay? Questions about this? Again, you really got to make sure that you understand this for the final. All right, now, I want to say something with this. I could then go further with this question. I could ask you, what metal is this? Because, like, imagine you're Indiana Jones, and you find some metal, right? And you're like, hey, I heat up this, I see how much energy does it take me to heat up this metal to 22 degrees Celsius, and I know the mass, and you do your calculation, you get that specific heat. So then what metal did Indiana Jones find? Lead. Good. There you go. All right. So, okay, so moving into, what is a calorimeter? Well, a calorimeter, it is a device that will measure how does the heat move from a hotter object to a colder object. So in other words, it's a device that measures the transfer of energy. How exactly is energy being transferred? And this is, they call it a coffee cup calorimeter. We could have done this lab, but we're just kind of tight on time at this point, and it's kind of whatever. But the idea of this calorimeter is I would have a really hot piece of metal. Okay, so picture I got a hot piece of metal. Like, ooh, that's really hot, and then I put it in a styrofoam cup that's filled with water. So then the heat from the metal will then mix with the colder water, and those two will come to like a normal temperature. The idea would then be I can calculate just how much of that heat moved from the metal to the water. So what's happening now is we can use the Q equals MC delta T to then set up two equations here to then calculate just how much of the heat goes from the metal to the water. So that's what they're trying to show here. Now, why is this negative Q metal? Why is there a negative sign there? Any thoughts?
You repeat the question?
Why is there a negative sign next to the metal? Why is it negative Q metal? Energy is being released. The heat is moving from the metal to the water. Think of it this way. Your parents, they hopefully have a lot of money in their bank account. If they give you $20, what happens to their bank account statement? It gets minus $20. That's why there's a minus here, because the heat is moving from the metal to the water. That's why the water is then positive. All right, then why is it a styrofoam cup? What's the purpose of the styrofoam cup? Why are we putting the hot metal and mixing it with the water in a styrofoam cup? Why not like a solo cup or something? You know, Ethan?
There's no loss of like.
Perfect. Good. Insulation. Because the idea here is you want as much heat as possible to go from the metal straight to the water. You don't want the heat to be lost to surroundings. So the assumption, and this is what the third bullet point is trying to say, the assumption is that when you do this, you put the hot metal in the water, none of that heat is escaping into the environment, which we know is not true, but for the sake of these calculations, that would be the assumption there. Okay. All right, let me show you how this would work. Like, now this is you won't see a problem like this on the final, just to be clear, but I want to still do it with you, just because I think if you can understand this, you can definitely understand the easier ones. And I think it's just worthwhile to kind of just see how you work with some of this stuff. So the idea here is what I said earlier: negative Q of the metal, and shorthand. We'll just say M for metal. Negative QM equals negative QW. We'll say W is the water. All right. Wait, negative. This is positive. Sorry. So then expand that out. Q equals MC delta T. So you would have negative M, we'll say M sub M. This little m is for the metal. So you'll have a mass for the metal. You'll have a C for the metal. Then you're going to have a delta T for the metal. Okay? That equals an M, a mass for the water, times a specific heat for a water, and then times a change in temperature for the water. Okay? So the idea would be there's 6 variables here. 5 of those variables should be up here, and then we can solve for the unknown. So let's go ahead and identify what we know, then we'll find the one we don't know. A 250 gram piece of metal, which of these variables would that be? This is first one. M sub M. Okay. Mass of the metal is heated to 100 degrees Celsius. Now, we have the delta T of the metal. Final mass initial. What would the 100 degrees Celsius be? That would be my final temperature and my initial temperature. No. That's the initial temperature. Now, to understand why that is yes, good, Stephen. The system is 40. You're like, what is the system? You're like, I hate the system. The system here is the metal and the water together. So the heat from the metal is being transferred to the water. So that system, when all of the heat from not all the heat, but when the metal and the water, the temperature between them gets at equilibrium, that will be at 42 degrees Celsius. That's why that is the final temperature. So 42 degrees Celsius is the final. So your delta T is negative 58 degrees Celsius. Why is it negative? True, but like actually understanding what's happening, why would that be so? What is that? What's that negative? What is that trying to represent? Yeah, releasing the heat. The heat is moving from the metal to the water, so that's why you're going down. It's negative 58, because heat always goes from hot to cold. All right, keeping it moving. 750 grams. What would that be? Mass of the water, MW. That is 25 degrees Celsius, so this would then be used to find the delta T of the water. But then 25, is that final or initial? Initial. So then what's your final? 42, good. So the metal and the water have the same final temperature. That's key to understanding what's happening here. They have the same final temperature because they are mixed together in this coffee cup, this styrofoam cup. Okay, so then delta T of the water will be 42 minus 25, which is 17. And then specific heat of the metal, that's our unknown. So C of M, that's going to be our X. That's going to be the thing we got to figure out. We know, last thing, the fifth thing would be the C of water is 4.184. So let's plug everything in and let's solve for the unknown. So negative, we got 250 grams. C of M, that's our unknown. Delta T of the metal is negative 58 degrees Celsius. That then equals the mass of the water, which is 750 grams. Specific heat of the water is 4.184 joules over grams degrees Celsius times delta T of the water, which is 17 degrees Celsius. Okay, so then, simplify and then solve for the unknown. So here, negative 250 times positive 58. I don't know. Let's figure that out. 14,500. Positive, right? Multiply two negatives becomes positive. And that's, units. What are the units there? Grams degrees Celsius. Okay. And then that times the C sub M. That then equals all that multiplied together. 750 times 4.184 times 17. 53,346. But what are the units? What are the units? Nope. Joules. Somebody said joules. Oh yeah, that's joules. Here's why. You have a grams here, and then on the bottom of the fraction there's a grams. So grams cancel, right? Same thing for degrees Celsius. Degrees Celsius here, degrees Celsius in the bottom, so those cancel. Okay? All right, and then home stretch. Divide both sides by the 14,500 grams degrees Celsius. And when you do that, the number you would get is 3.68. Now, what are the units? Multiple answer choice with 3.68. How do you know the units? Yeah, good, Max. Joules over grams degrees Celsius. I know that was really long. Again, I won't give you one like that on the final, but if you can understand this, then everything else is very simple, So, all right, you got a few problems for you to work on to finish up the rest of this worksheet, and then there's some predicting products practice. So at the end of this slide deck, I have those notes to help you with predicting the products. So take a look at those.